plan in this lecture is to talk about the Mobius strip, but whenever we talk the Mobius strip, we start by talking about the cylinder. And we're going to sort of go through the cylinder using our notion of quotient spaces and some other facts. And it's a very important place to start, and we're going to understand the cylinder as a quotient space. And the way we begin is with a square. And this square we're going to use to produce all kinds of interesting things ultimately if we get to them. But the square is defined in terms of a set theorist or a topologist as the Cartesian product of two closed intervals, 0, 1, 0, 1, which is a subset of R2, which is defined as the Cartesian product of two real number lines. So the idea is that this is a subset of R2, and we know how to that this is defined by the set of all ordered pairs A and B, where A is an element of an interval 0, 1, and B is the element of another interval of 0, 1. And note, these are closed intervals, right? These are actually closed intervals on the real line. And this is clearly a subset of this, which is simply defined as two numbers, A and B, where A and B are both elements of R. And so this is not the cylinder, right? This is just a square, a closed square, a square that contains its boundary and lives as sort of as a subset in R2. And starting from this cylinder, or starting from this square, as it were, we're going to actually produce a cylinder systematically using our understanding of quotient spaces. So also, now we are going to introduce a map. We're going to call that map phi, and phi is going to be a map from the closed interval 0, 1 squared, which is what that is, right? That's the same thing. And it's going to be a map into R3. And this map is actually going to be our cylinder. The way this works is, since this object here is a set of ordered pairs, right? Since this object is a set of ordered pairs, we can view phi as a function that takes two numbers, A and B, and gives you, it has to give you a point. It has, since this is a point in R2, or in the square, if it's in the square here, it's this, I'm sorry, this is a point in the square. This has to be a point in R3. So this is going to be an ordered triplet, right? And that triplet, for example, could be cosine 2 pi of A, sine 2 pi of A, and then just B, right? And we would think of this as sort of X, Y, and Z, and it's not too hard to see that that actually is a cylinder, right, in R3. So what we've done is we've created a cylinder in R3 using the domain of points in this square. And this is how we did it. We use this function. And the actual cylinder itself, we're going to call a set C, which is the set of all points X, Y, and Z, which is an element of R3, such that X squared plus Y squared equals 1, and Z is an element of the interval 0 to 1. And that, move this over a little bit, that is the cylinder. So this is the cylinder here. So the name of the game, because we want to kind of show this, the cylinder is actually a quotient space of something, is we need to show that this set is homeomorphic, or this, well, it can't be homeomorphic. Why can't this be homeomorphic to anything? It's because it's not a topological space yet. All it is a set. But once we make this into a topological space, we need to show that this topological space is homeomorphic to some quotient space. And that quotient space is going to have, this is an underlying space with an equivalence relation that we're going to develop. So we're going to show all that, right? But right now, this is the cylinder as a set. And so how do we topologize that set? How do we make it so that this is an actual topology? Well, the way we do it is we give it what's called the subspace topology. Which means since C is a subset of R3, we use the standard topology on R3. The standard topology on R3, which is, of course, the set of little open balls, which would be little open spheres. That would be the base of the standard topology of R3. So the standard topology here is the set of all little open spheres, and those open spheres form the base of the standard topology of R3. Well, C is a subspace of R3. So the topology on C will be the intersection of all these open balls in R3, the intersection of that with this subspace. And what that's going to end up doing is inducing on the cylinder. You can imagine, well, there's an open ball here. Well, that has no intersection with C. This is C here, right? So that does not inform us at all about an open set on C. But if you had a sphere here that actually intersected the surface, kind of penetrated the edge of the sphere, the portion of C that actually is inside that open ball, which is sort of a slightly curved surface of C, that would count as an open set on the set C. And that would be true for every open set out here in R3. Every open ball will have some intersection on this cylinder. Notice the caps of the cylinder aren't part of it. There is no cap here. It's just the tube that extends from 0 to 1, say, and the circle is defined by x, y equals 0. Now notice that the top, right, this top edge is closed, right, because I'm using this, the equality of 1, so the surface is the actual surface where x plus y equals 1, but the z goes from 0 to 1, so that includes 0 and 1, right? So this upper edge is part of the cylinder, and therefore the open sets on this cylinder, the way we've defined it here, are going to actually include, they won't include this. Let me draw that better. Let me draw a little better. There's a sphere that's going to sort of include this part of the cylinder. This area here will be open, meaning it won't include that because the ball, right, is open. But this interior line is actually part of the inside of the ball. So that actually will be part of the open set. So the cylinder has open sets that include these points on the boundary edge. Anyway, that's the subspace topology on the cylinder. So now the cylinder with this subspace topology will actually be a topological space. And as such, we can now start thinking about finding other topological spaces that are similar to the cylinder. So now, the next thing we want to take a look at is we want to see how this function here relates this set here, which is this set right here, the square. We want to see how this function relates the square to the cylinder. And the most important thing to notice is, first of all, it is continuous, right? It is going to be continuous because every, this is just a continuous function, right? This is a nice, smooth, continuous function that takes a point in the square and gives you a point on the cylinder. And it will take open sets on the square and give you open sets on the cylinder. Or the other way around too. It'll take open sets on the cylinder and give you open sets on the square. That's what's important, right? It's the inverse of this function that defines its continuity. So we need open sets on the cylinder to map to open sets up here. By the way, this object also has the subspace topology, right? We haven't topologized this thing either, but it's even easier to see here because now I just look at open balls in the plane R2, and those open balls form a base of the topology for R2, and the intersection of those open balls with R square, for example, that piece, well actually I should draw it this way, dot, 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 this piece, and this piece, those are all open sets in the square based on the subspace topology, and those open sets on the square form a base of the total topology of the cylinder. So we've topologized both the square and the cylinder with this subspace topology. But what's important is that we understand that the inverse of this, right, the inverse of this will take any point on the cylinder and give any open set on the cylinder and give you an open set up here. And you can show that, and showing that will let us know that this is a continuous function. But also, not only is it continuous, it's also surjective, right? So we know it's continuous, but it's also surjective, which means it's onto. So the entire cylinder is covered by the points A, B that are defined by the square, which is important, right? Because when we talk about quotient spaces, the quotient maps are always surjective maps. So the idea that we have a surjective function here could be important, but it is important to note that this is a surjective function and it's a continuous function. But what is it not? It is not injective. Right? Injective means one-to-one. And the reason it isn't injective is because the points 0 and 1 for A will both graph to the same point on the cylinder. So, for example, if I take A equals 0, the cosine of 0 is 1, and the sine of 0 is 0. So I'll get 1, 0. If I take 1, the cosine of 2 pi is 0, and the sine of 2 pi, the cosine of 2 pi is 1, and the sine of 2 pi is 0. So it gives me the same point. So these points over here, where if we understand this to be A, where A is 0 and A is 1, they graph to the same point over here. So that one part, that one mapping, so when A equals 0 or 1, we have a 2-to-1 mapping. So it's not injective. So, so that's too bad, right? I guess the way to write this, by the way, is phi of 0b equals phi of 1b, right? And that's just simply 2-to-1, right? So it's not, which by the way equals the triplet 1, 0, b. Okay, so that's just a 2-to-1 mapping. So this question about being injective, we could make it injective if we wanted to, and and we simply do it with an equivalence relation, right? Let's do it this way. We will say we'll create an equivalence relation that is going to turn that mapping phi into an injective mapping, and the way we're going to do that is we're going to simply say that 0 and b is equivalent to 1b. Right? And you can check that this is an equivalence relation. I mean you check that it's reflexive, symmetric, and transitive, right? So this is an equivalence relation. And and this will be true for all B that is an element of 0 and 1. So for every B, 0B is going to equal 1B for any B that's in the interval 0 to 1. And once we have this equivalence relation, and we're convinced it's equivalence relation, we quickly form the quotient space, and I'll call the quotient space X. And X is going to be 0, 1 cross 0, 1 by the equivalence relation above, right? The one we've described. And it's now going to be a quotient space once we give it the proper topology, right? Usually the word space is reserved for sets that have topologies, although sometimes I've seen space just used for regular sets. But I like the idea of saying a set is a space if it's at least, at a minimum, topologized, I guess is the right way to say it. This, by the way, can also be written as 0, 1 squared with the equivalence relation. So all means the same thing. So now we're creating this object that we're creating sort of a structure, a mathematical structure of things, where we started with this set, and now we've created this set, and we have the set C, the cylinder, right? And that was defined as, the set of all x, y, z, such that x squared plus y squared equaled 1, and z was an element of 0 to 1, right? So we have 3 different sets, like this. And we have a map that goes like that, and that map was phi. And we have a map that goes like this, and which is the natural projection map. The natural projection map, because we are now going to topologize this with the quotient topology, and these two have the subspace topology. Subspace topology, SST, how about that? And so this is sort of the circumstance we're dealing with. Now I want to prove, ultimately, that the cylinder, this quotient space, where I've identified, so you may remember we had a square, right? And if this is A and this is B, B obviously goes from 0 to 1, and A goes from 0 to 1 too. This is the square with the subspace topology on the square. I've taken this line and I've identified it with this line, right? If A is 0, then any value of B is going to equal the same value of B when A is 1. So this point is identified with that point. That point's identified with that point. And if every point on this line here is identified with points on that line there, and they're jammed into the same equivalence class, every point on this line and every point on that line is jammed into the same equivalence class, and every point in here is its own equivalence class. And it's actually important to say that. Like I should say, I should say 0B is equivalent to 1B, and then I should say AB, the equivalence class of AB simply equals the set AB if A does not equal 0 and A does not equal 1, right? So any other value of A, the equivalence class of that object is just AB. On the other hand, the equivalence class of 1B equals the set of 1B and 0B, right? So all the equivalence classes of this cylinder are almost all, the vast majority of them are just singletons that have the ordered pair of points, AB. But anybody that's on, any point that's on this line or this line, the equivalence class contains 2 points. You might want to say, oh, this line is made equivalent to that line. But this line, not every point on this line belongs to the same equivalence class. Because remember, B is part of it, right? So, you know, if B is 1/2, that point's equivalent to that point, but that point is not equivalent to that point, right? It's not like all these points on the line are made into a single, put in a single set. Only the opposing points are, right? And in the Mobius strip, that point's made equivalent to that point instead of that point, as we'll see later. But, so those are the equivalence classes we're dealing with. And so the projection map P is a map that takes 0, 1 squared into 0, 1 squared by the equivalence class, and P maps A and B. P of A and B equals the equivalence class for A, B, like that. So PAB is overwhelmingly, as we just said, mapping singletons to singletons, but it does map these to sets that contain 2 items. But that's and so that's how we write down the projection map. It's a simple, straight up projection map. Now, is the projection map continuous? Well, to answer the question, is the projection map continuous, you have to know, does the inverse of the projection map map open sets here to open sets there? So every open set here under the inverse projection map had better be an open set up here if, in order for P to be continuous. Because remember, continuity is always driven by the inverse function. So, well, if we apply the quotient topology like we have, if we apply this quotient topology, then by definition P is inverse, right? Because that's the whole point of the quotient topology. The quotient topology is such that the pre-image of any open set here is an open set up there. So we've given this the quotient topology, therefore P is continuous. All right, and now we're kind of getting close to what we want to be able to do. What we want to be able to do is talk about a map from between these 2 spaces. And what we've done is, remember, this map was not injective. It was surjective and continuous, but it was not injective. But this map can be, we can make a map from here to here that is injective and is very familiar. I'm going to make the map, I'm going to call it phi with a tilde. And phi tilde operates on, phi tilde is going to be a map from here to here, and therefore its domain is items of this space and its range is items of that space. Well, what are the items of this quotient space? Well, remember, the elements of the quotient space are the equivalence classes, of the underlying set under this projection. And the projection, of course, is constructed by this equivalence relation. So this thing takes equivalence classes and gives you points in C. So let's define it so that it takes an equivalence class. Say it takes an equivalence class. Well, here, how would we write that? That's actually kind of interesting, right? Normally when we take a function, we say phi, and then we put parentheses, and inside the parentheses we put the argument. Well, what's the argument? Well, the argument is an equivalence class. So in this case, it's an equivalence class A and B. So that's kind of what the argument looks like. It's a bit confusing because you have these parentheses inside the parentheses, right? So you could also just forego the outer parentheses, right? As long as you understand what you're doing, and you could write it this way, right? Something like that. But either way, it equals. It's going to equal the function phi acting on AB, right? So whatever equivalence class you choose, you feed it to the tilde function, and the output is the same as the regular phi function on the representative of the class. And that function, now, that function is one-to-one, right? Because the only troubling point was this one up here. This one here, where 0 and B and 1 and B, those were the ones that mapped 2-to-1 in the old circumstance, right? Under phi, those points are 2-to-1. But here, they have the same equivalence class. So this function here is going to be 1-to-1. This function's actually going to be injective. And it's going to be surjective, right? So this is now injective and surjective, which means it's bijective. Nice. And then the question is it continuous? So the question of its continuity is the next thing we need to turn our attention to. And in order to do that, we're going to cover a slightly different example because we need to understand a slightly different principle that we will now apply as a theorem to that. And that principle will look like this. If we have, oh, I've made my point a little small. Let me see if I can up it a bit. That's better. So if we have a topological space X, and we have a continuous function P to a topological space Y, and then we have a topological space Z, and a function from Y to Z, which we'll call F, and then X to Z is going to be F after P, like that. So there's a universal property that when P is when it's a quotient map, right? When P is a quotient map, we can establish this interesting property that F is continuous if and only if F after P is continuous. Now, if P is a quotient map, remember that means that Y has the quotient topology. I'll write it that way. X has some topology, right? X and the topology of X. And Z has some topology, Z and the topology of Z. But Y, we have to make sure, has the quotient topology, right? So in order to show this kind of statement, you have to show two things. You have to show that if F is continuous, then F after P is continuous. And you have to show that if F after P is continuous, then F is continuous. So to get the if and only if, you got to show, you assume this, prove that, then you assume the continuity of this and prove the continuity of that, and then you assume the continuity of that and prove the continuity of this. So one step is actually pretty easy, because if X is a topological space and P is a quotient map, well then Y, having the quotient topology, P is definitely continuous. So if we assume the continuity of F, and we're given the continuity of P, well, we happen to know that the composition of two continuous functions is continuous. So if P is continuous and F is continuous, then F after P is continuous. And that's because the composition of continuous functions is continuous. Now, this is a little topological rule that you probably may or may not specifically remember from when we talked about continuity. I don't even know if I actually specifically said this when we talked about continuity, because there's a lot of different theorems about continuity we could have talked about, and this isn't a full topology course. But that's sort of the way it goes. When you do proofs, like I want to prove this principle, I'm going to go through steps that involve other topological theorems that we haven't really proved, but are plausible, but still you have to actually prove that the composition of continuous functions is continuous. You know, things that are easy to say and sound obvious are not always true. Now, you may have learned this from calculus, that this is the case, but does that mean it's true generally speaking in all of topology? Because calculus, remember, depends on the usual standard topology of Euclidean space. And now we're talking about arbitrary topologies. As long as it's a topology, That's all we need to know. We need to know it has the properties of a topological space, but it doesn't have to be the topology of Euclidean space. But even still, under our definition of topology, this logical notion is true. So continuous functions are supposed to have properties like this, but still this has to be proven. Now, I'm not going to prove it, but it is. But the point is that you can look this up very easily, and if you don't know this, it's no big deal because you're not expected to know every single theorem of topologies that's out there. And we're going to run through about 3 or 4 in a minute or two, and you're not going to know those either. Well, at least I didn't know them. And the point is you get a feel. To prove this, you use open sets, closed sets, you use functions between sets, all that kind of stuff. But anyway, so I've proven this in one way. I've assumed f is continuous, and I easily proved that f after p is continuous because I know that the composition of continuous functions is continuous. Now let's do it the other way around. Now I'm going to assume that f after p is continuous, and I want to prove that f is continuous. So how is that going to work? So I'll begin with a set W, which is an element of the topology of Z. That's another way of saying W is open in, W is open in Z. Okay? So I start with that. And once I know that W is open in Z, I have assume F after P is continuous. Well, what does that mean? Well, that means that the inverse of f after p, acting on an open set in Z, must be an element of the topology of X, which means is open in X. Right? So the assumption that this is continuous, by its very definition of what it means to be continuous, it means that the inverse takes open sets in the range of the function and gives you open sets in the domain. So therefore, the inverse, f after p inverse, which is a function from Z to X, must take an open set in Z and give you an open set in X. And that's what this statement says. So this statement is really nothing more than the definition of continuity. So what does this thing actually look like if we were to draw it in this other form of notation? Well, it would look like F inverse W P inverse acting on F inverse W, right? Because I would take an open set. I bet maybe I'll just draw my little open set here. How about that? There's W right there. That's W. So that's my little open set in Z. Well, so F after P, right? F after P takes a set in, takes points in X, runs P, and then runs F. So F after P inverse runs F inverse, then runs P inverse. And that's what this is. It runs F inverse, and then it runs P inverse. Okay, so, but we know that this thing, right, since it's a restatement of what's written right above it, that's an element of the topology of X. So it is open in X. And that's not even very conclusory. That's literally just a rewriting this in a different notation, right? So, but here's the important point now. Now we use the fact that P is a quotient map, and Y has the quotient topology. And remember what that meant. That meant that O is open in Y if P inverse of O is open in X. And remember, that was slightly different than continuity, right? So, but that's exactly the case we're faced with here, right? We know that P inverse of this thing here, we know that P inverse of this is open in X, which means under the quotient topology, that must be open in Y. And I'm being redundant here. When I say, just to emphasize this statement that the preimage of W in Y is an element of the topology of Y, that's the same thing as saying the preimage of W is open in Y. All right? Now, once I know that if W is an open, basically remember, W is an arbitrary open set in Z, right? But now I know that the preimage of an arbitrary open set in Z is an open set in Y, right? The arbitrary image, the preimage of an arbitrary open set in Z is open in Y. That means that, and that's true for the arbitrary, so that means that F is continuous, right? Because the arbitrary preimage of an open set under F is an open set in Y. So I've now proven that F is continuous. Therefore, F is continuous. So now I've proven both directions. So now I know that if P is a quotient map, remember we used the fact that it was a quotient map because it depended on the quotient topology here in this step, going from here to here, right? In other words, the only way I could say that this preimage was always open in Y is because this is a quotient map, and the definition of the quotient topology demands that that's the case. But the point is I've now shown that F is continuous. So when P is a quotient map, I know that F composed with P, and that F will be continuous if F composed with P is continuous. Okay, so now we're going to apply this to, this situation here. And let's see exactly how are we going to do it. Well, what we're interested in showing is, let me actually erase this because I'm not quite sure which direction I want to move, right? But I do know, all right, so let me lift that up, and then I'll draw it in blue. So we started with one set, and we had a quotient map P, right? Let me move it over a little bit. So this was sort of this is the set we called X. Well, we're now going to call that 0, 1 squared. Then the map we called P, which is our quotient map, well, that's clearly the set we were calling Y, which is going to be 0, 1 squared by the equivalence relation. Then we clearly have the set C, which is the cylinder. And we have this map here, which is the map phi, right? That's the map phi, which is the mapping from the square to the cylinder. That's going to play the role, and then there's going to be this map here, which we'll call F. So phi is going to play the role of F after P, right? And now what do we know? Well, we know that this is continuous and a quotient map, and we know that this is continuous. So by the theorem we just did, F is continuous if and only if this guy is continuous and this guy's a quotient map and continuous. So now we know, based on the structure we did before, that F is continuous. So that's important because now if I go back to this picture here, I now know that this map here, actually, so this is phi bar, right? Phi tilde. Phi tilde is continuous. So now I can say it's injective, surjective, which means it's bijective, and it's continuous, right? So that's pretty good because it's almost a homeomorphism. And remember, that's what we're after. We wanted to show that the quotient space of the square under the equivalence relation that links these two sides together, we want to show that that is homeomorphic to the cylinder, which is by definition of a cylinder, this set here. Well, what we've got is we've got bijectivity and continuity of a function from the quotient space to the cylinder, but what's missing? The only thing that's, so this isn't quite a homeomorphism, because in order for it to be a homeomorphism, it has to be bicontinuous. So phi tilde inverse has to be continuous, right? And so we have to prove that the inverse of this function, which is phi itself, takes open sets from here, and gives you open sets from there. Because that's the inverse of the inverse. So we have to make sure it's bicontinuous. So we could try to prove that. We could try to prove that this is continuous this way, and it's continuous in the other way too. And then we would prove that these two are homeomorphic. But we're actually not going to do that. We're going to use a very famous trick in topology. And I shouldn't say it's a trick. We're going to use a theorem in topology that you probably don't know, but is very useful in this circumstance because this circumstance comes up enough that we use this theorem. And that theorem goes like this. It basically says if you have a bijective and continuous function between a compact space and a Hausdorff space, then that function is a homeomorphism. So let's have a quick look at what that's all about. So now we're going to divert again and talk about this idea. We have a space, topological space X and a topological space Y with a function between them. That function is f, and we've decided it is bijective and continuous. And remember, ultimately, of course, this is going to be 0, 1, the quotient space, and this is going to be the cylinder C, right? But we're speaking about things in general right now. But X has to be compact. So for this theorem to apply ultimately to our situation, I'm going to have to eventually show that's compact, and this has to be Hausdorff. Now C is, I'm not going to bother showing C as Hausdorff, right? It's the surface of a cylinder with the standard induced topology, and that is Hausdorff, right? That's, I mean, the topology of R3 is Hausdorff, and so the induced topology on this cylinder is not too hard to show as Hausdorff. We will talk about the compactness of this thing later, but the theory that we're after, and I'm going to erase these so they're not distracting us, because this is a more general theorem, is that whatever the spaces are, if the domain space is compact and the range space is Hausdorff, and F is bijective and continuous, then F is a homeomorphism. Now, the only thing missing from F just being a homeomorphism outright, of course, is that it has to be bicontinuous, bijective and bicontinuous, which means we need to know that F inverse is continuous as well. So, as a reminder, for F to be continuous, that means F inverse maps open sets in Y to open sets in X. And therefore, because F inverse is open, therefore F is continuous. So for F inverse to be continuous, F has to map open sets in X to open sets in Y. And that's, of course, what homeomorphisms do. They take open sets to open sets in both directions. Homeomorphisms are functions, right? Homeomorphic functions take open sets this way and open sets back. So all that's left to show is that given the compactness and the Hausdorffiousness, then F inverse will be continuous as well. So how are we going to show that? Well, we're going to show that using a bunch of other topological theorems that I'll state but probably won't prove, but it just gives you a feel for how this is going to work. So remember that a compact space means that every cover has a finite subcover. So one thing that's true is if I take an open set in X, say I call it V, right? And well, actually, what I'm going to do is I'm not going to take an open set in X. I'm going to take a closed set. I'm going to take a closed set in X, and I'm going to call it V. And I'm going to now assert that V, which is closed, is a subset of X, and V is compact. Why is it compact? It's compact because the closed subspace of a compact space is compact. So there's a topological principle out there that says, hey, if I have a closed subset of a compact space, like I do here, I've asserted that V is closed because I want to exploit this rule, that subset is compact. So I now know that V, this little subset, this closed set of X, is compact because of this rule. And that rule is its own proof. I mean, I could do this by hyperlinks, right? We could hyperlink this, and then you could get a whole proof of why a closed subspace of a compact space is compact. It's not a difficult proof. You could look it up anywhere. But knowing that theorem, I can now assert that any closed subspace of X is compact because X is compact. So given that, I now can project F into Y using F. I'm sorry, project V into Y using F. FV is a subset of Y, and guess what? That subset, F of V, is compact. And why is that? That's because the continuous, man, I don't write well, but geez, I can do better than that, right? The continuous image of a compact set is compact. Right? That's another topological rule. If I have a continuous map, and I have a compact set, that continuous map preserves the image of that compact set will also be compact in Y. The continuity is strong enough to guarantee it, right? Homeomorphisms make sure that everything in X is the same in Y, but continuity will preserve some things, and one thing it preserves is the compactness of things. And again, that's a hyperlink topological proof that you could prove, but it's a simple one. So now I know that F of V is compact. Now I know that Y is Hausdorff, right? So what do I now know from that? F of V is closed in Y. Well, it's F of V is closed. That's enough, right? I don't need to say in Y because F of V is obviously in Y, but it's common to say it's closed in Y just to help you remember that F of V lands in Y. But how do we know that F of V is closed in Y? Well, because I know that compact subspaces of Hausdorff spaces are closed, right? I know that compact subspace of a Hausdorff space is closed. And that, again, is a little topological rule, just like all these others, that you learn from studying compact spaces and Hausdorff spaces. You learn that any compact subspace of a Hausdorff space will be closed. Not a difficult proof either, but something you need to know for this, because we started with a closed set in X, and we knew that because it was a closed subspace of a compact space, we know that that closed set was compact. Then we use a continuous mapping of a compact space, so we know that the mapping over here, which is F of V, we know that that is also compact. So we now know that this is compact. And we know that it's closed over here in Y because Y being Hausdorff, there's this rule. The compact subspace of a Hausdorff space is closed. So we know that. And then lastly, well, what does that mean? Well, so remember what our goal was. Our goal is to show that F inverse is continuous. Well, we need the inverse of the inverse, so we need to show, so the continuity of F inverse is going to be driven by F and how F handles closed and open sets. Just like the continuity of F was decided by whether or not F inverse mapped open sets to open sets, or equivalently closed sets to closed sets. We're actually going to use the definition of continuity that says the inverse function must map closed sets to closed sets. So now we're interested in F inverse's continuity, and so we got to look at F. Well, we now know that F of V is closed in Y, and by our presumption, V we know was closed. We started with the presumption that V was closed. So F of V is closed. So we know F takes closed sets and gives us closed sets, which proves that F inverse is continuous based on F inverse is continuous by the closed set version of the definition of continuity. And so now we know that since F, which is the inverse of F inverse, takes closed sets in X and gives you closed sets in Y, we know that F inverse is continuous, and therefore we know this function is bicontinuous. And of course, the bicontinuity plus the bijectivity means that F is in fact a homeomorphism. So we're going to use that to go back to our original problem of the cylinder now. So with that in mind, we go back to, by the way, there's a sheet in here I did not use. I don't want you to think you missed something. When I scroll between these sheets, there's one in there that I screwed up and am not using. So now back here on this screen, we showed that F was continuous, and now if we can show that this is compact, we know this is Hausdorff, so that's good. Now if we can show that this is compact, then our rule will apply and F will be bicontinuous, and therefore we will have established a homeomorphism between this quotient space with the cylinder. But that's not hard at all to do because this map is a continuous map, and this is a compact space. So the continuous image of a compact space is going to give you compact spaces. Now, there could be a problem that if P didn't map into this entire space, right? If all of X didn't map into all of Y, or most of X didn't map into all of Y, the whole point is Y has to be completely covered. But by definition, it's a surjective map, right? It's a quotient map. So it's surjective. So you know that all of Y is covered, and it's going to be, and since P is a continuous mapping, you know that it's going to preserve compactness. So if this is compact, then so is this. But you know this is compact, which is why we actually chose it as the closed square. This is a compact subspace of R2, so this object is compact. So now we've basically got it. This is compact. This is Hausdorff. Therefore, F is a homeomorphism. And that is the touchstone. That's what we're after. That being a homeomorphism is guarantee that we can now say that the cylinder here is homeomorphic with this particular quotient space under, which is this base set under the equivalence relation that links those two edges together. And that homeomorphism allows us to sort of say the cylinder is quotient space itself. I mean, once you have a homeomorphism, right, now I basically can do this. We basically are now saying that these two sets are in the same homeomorphism class, right? They're basically identical, topologically speaking. So, and that's the proof. So the point wasn't to sort of dazzle you with amazing statements of topology, but it's to show you that when you do these topological proofs, you end up having to use facts like the composition of continuous functions are continuous. You have to use facts that you have to use the definition of the quotient topology to prove certain things are open when other things are known. You have to know, the closed subspace of a compact space is compact. The continuous image of a compact set is compact. The compact subspace of a Hausdorff space is closed. These are all facts from topology that aren't proved idly. They're proved for this purpose. And the ultimate goal is to be able to assert things like this, like a cylinder is a quotient space. All right, so let's see how we're doing. So I think we've gone far enough. This has almost been an hour, and the next thing is to kind of do a lot of this exercise or a similar exercise for the Mobius strip. I want to get a little bit back to, we've done quotient spaces, I want to get a little bit back to just sort of using that concept for the definition of a Mobius strip. I want to prove that the Mobius strip is a differentiable manifold, and I don't know, maybe we should do some other examples after that, but we're going to stop with the cylinder here today, the goal having been just to prove how we can show that this square under a particular equivalence relation, right, a particular equivalence relation will give you something homeomorphic to a cylinder. So the square is the quotient space of a square under a particular equivalence relation gives you a cylinder. And now we can play around with the square in multiple different ways. In this particular case, what we did was we took the square and we took this side and we made an equivalence relationship with that side of this nature, and we left the top and the bottom alone. But every possible combination exists out there. The Mobius strip is when we do the same thing, but we flip it so that we're establishing an equivalence between that point and this point, and this point and that point. So the equivalence goes like that, and that will be a Mobius strip. But we can do a lot of other things, right? We can make a sphere by making all of these equivalent. Wait a minute, how do we do that? They're all equivalent. All these arrowheads would be equivalent, and we would have a sphere. That's not even the right way of doing it. If I take if I take all of these points here on the boundary and make it into a single point, right, which is different than this. Here it's these points are equivalent and these points are equivalent, but these two lines are actually full of different equivalent points. Here, if I take this whole boundary of the sphere and I turn it all into one point, right, that will be equivalent, homeomorphic to a sphere, it turns out. And then, but I can do other things, right? I can take the square and I can take these two sides and I can take these two sides as I would in a cylinder, and I can make a Klein bottle, right? And the most interesting is if I reverse that, right? If I take this top side and I flip it to be the opposite direction, so I'm equating this point and this point and this point and that would become a projective plane. Projective plane. All of these things are topological manifolds, and they're all definable in terms of quotient spaces and equivalent relations. We'll run through the Mobius strip next time. Okay, we'll talk later.